Okay, this is a max power transfer problem. Max power transfer for AC, complex power. So the basic idea here is you want to balance the impedance, specifically the reactance of the source and the load. Okay, so if you have a positive reactance on the source, you want to have a negative reactance on the load so that the reactances cancel out and the overall circuit is resistive. So that's the basic idea. There's also some kind of neato tricks in here. So we've got a sinusoidal source Ig given by I sub g is 3 cosine 5000 t in amps. That's this guy, I sub g, and there's a 20 ohm resistor. There's a 8 microfarad cap. There's an inductor up here, 3.6 millihenries, and another resistor, 4 ohm over here. Okay, then we've got these terminals A, B. We're going to connect a load across A, B. We haven't done that since chapter 4, but we're going to do that. So we want to find what is the impedance of the load, or Z load, for maximum average power transfer. So they're asking for P. When they ask for average, they're asking for P. And part B, what is that P? What is P of the load going to be for that? For this Z condition, for this impedance of the load, what's the power going to be? And then C, what is the resistance of the load for max P load for a purely resistive load? So first they're going to ask for an impedance of the load that gives you a max P. Then they're going to ask, what is that P? And then they're going to ask, what is the resistance of the load if for max P on the load if it's a purely resistive load? That is not impedance, but just resistance. Okay. And then lastly, what is that P load? For that condition. P load with, so basically asking for P load with Z of load, and then P load equals what with R of load. So basically they're just asking for two different real powers, one with an impedance load and one with just a purely resistance load, basically. So so the condition for maximum max power transfer is the impedance of the load needs to be equal to the complex conjugate of the impedance of the Thevenin equivalent. In other words, whatever reactive component is in the distribution side, the Thevenin equivalent circuit, which is our distribution side, whatever reactance is in there, we want to reverse the sign of that in the load so that the reactances on the source and the load cancel each other, and we have an overall resistive circuit. That's the condition for sending maximum power transfer. So we need the we need the phasor domain equivalent of this circuit. And specifically, we need the phasor domain Thevenin equivalent. Okay, so let's do that. So we're going to also use this open eyes, short V's thing. Remember that? This is the method for calculating the Thevenin equivalent. So here's our an eye source that's open that. So we'll open that. All right, there's this eye. We're just going to open it or take it out of the circuit, make it like an open circuit. And then at the same time, I'm going to put in the phasor domain equivalent for this thing. So this is the 20 ohm is just 20 ohm, but the 8 microfarad, if you do the calculations, which I'm going to skip, if you do the calculations at 5000 T and calculate the impedance for this cap, which we've done before, it's not that hard. You end up with minus J40. Then this inductor likewise ends up being J18, and this resistor just comes straight across as 4 ohms. So we've got this situation here just by opening the eyes and shorting the V. So opening the eyes, all we have is an eye, and then doing the phasor domain equivalents of these elements over here. And then we can do some neat tricks. So this guy here, these guys are in parallel, right? So 20 times minus J40 over 20 plus minus J40 is going to be 16 minus J8 ohms. Okay. Now we could put that in there and then add up these this thing here with these other two which are in series. The J18 and the 4 would be in series with this 16 minus J8. We could do that, and that would be the Thevenin impedance, but we still need the Thevenin voltage, and we would have to calculate that by some other method, similar to what we've done in Chapter 4, but using phasors. So we could do that, but just to point out that we could do a little trick and sort of save a little time. So we'll put this 20 and the minus J40, which we calculated the parallel equivalent of. We'll just put that in this little box here, and then leave the J18 and the 4 hanging out over here between nodes A and B. And see if we put this guy back in here. If we put this 3 angle 0, which is now the phasor for this time domain current signal, we put that back in here. If you do that, and then if you do a source transform, you're almost to the Thevenin equivalent, the voltage and the impedance. So do a source transform here. It's just a chance to do a source transform in phasor domain. So, and if we did that, then we'd have a voltage source in series with this impedance, right? Because right now we have a current source in parallel with an impedance, and the source transform, you just change current in parallel with impedance, you change that to voltage in series with that same impedance. And if you do that, you're going to end up with a voltage source, which is going to be the V Thevenin in series with that same impedance. So it's 16 minus J8. All right, and then the J18 will still be here, and the 4 will still be here between nodes. Here's nodes A and B. So if you did this source transform, you basically have the V Thevenin. You still need Z Thevenin, but that's just these guys in series. All right. So the calculation, the source transform, Ohm's law, right? You just use Ohm's law to get this this V. It's going to be I phasor Z. So it's going to be 3 angle 0 is the I, and this Z, 16 minus J8, right? So this is what a source transform looks like in complex, right? We're just converting this current in parallel with an impedance into a voltage in series with that same impedance, and we solve for the new source, which was a current, now it's a voltage. We solve for that using Ohm's law. That's just what we were doing in chapter 4, but now we're just doing that with phasors. So you end up with 53 angle minus 26.37 volts. And you add up all the z's, and it's just going to be 16 plus 4 is 20, and then this 18 and minus 8 is going to be 10, so it just looks like this. This ends up being, so the 16 and the 4 is just a 20, and this becomes it's like it was an inductor, because it's going to be positive 18 minus 8 is positive 10, which is positive, which we associate with an inductor. So there's that guy, and the V sub Thevenin is still here, and yeah. So this is the Thevenin equivalent right here. This thing here. This is the Thevenin equivalent circuit, which anytime you're doing a maximum power transfer problem, you need to calculate the Thevenin equivalent. Okay, so that was a little trick using a parallel combination and then a source transform, which leads directly to the V Thevenin. And then we add up these resistors to get the R or the Z Thevenin. Now, this source transform was an opportunity to do a little trick, but if we hadn't have done that and we would have just kept this open I thing, then we would have combined these three elements and to get the Z Thevenin, but then we'd still need to calculate V Thevenin by some other method, voltage division, or some other few steps, which is good, but just another way to do it. Anyway, now we have the Thevenin condition, so we can apply our condition for max power transfer, which is the Z of the load is the Z Thevenin conjugate. So this thing's here, and basically this, what appears to be a J10 inductor, we want to cancel that out with a minus J10 cap. Then that's this conjugate thing, right? This is 20 plus J10. The conjugate of that would be 20 minus J10. Okay, and what's in effect happening is this inductance of the distribution circuit is being canceled out by the capacitance of this load, and the overall circuit appears to be a 40 ohm purely resistive. Okay, so that's the trick. So we can calculate power, the real power, which, by the way, all the real power is going to come off in here, right? The P of the load is due to the resistance only, right? It's a Q. This would, these two cancel, the inductor and the cap cancel, but if they didn't, there would be some Q in here. But there's no Q because these guys cancel. But generally speaking, any real power comes off of just resistors, right? Because power is it's leaving the system, and we model that with a resistor. Q's are just going back and forth, but once again, here there's no Q. So if we had I in phasor, then we could calculate the power leaving right here. So so Ohm's law, I is this V phasor over the Z total, right? Total. So it's going to be this V Thevenin is 53 angle 26 minus 26. It's going over 20 plus J10 plus 20 minus J10. These cancel. and it's just 53 angle minus 26 over 40 ohms. That's right. So the whole circuit here, but with these two reactive elements canceling each other, just appears to be a 40 ohm circuit, right? So just the voltage divided by 40, basically. So this is 1.34 angle minus 26 amps. Then we have this formula for power in a AC circuit. We need RMS values squared R. Right? We need to use RMS values for real power calculations. That's why kind of the reason we have RMS values, at least speaking as an engineer doing power calculations. They're very useful for that. So so IRMS is just I peak over root 2, which is 1.34 over root 2. Power, running out of room here, but power is 1 over 3/4 root 2 quantity squared times 20, because we just want the power coming off of here. We use 40 to get the total, the total resistance to get the current, right? We used 40 to get I, but now we're just interested in the power coming off of here, so we use the current through this, and we need to use the RMS value, just using I squared R variation. Anyway, this is 20. This works out being to be 18 watts. So what's happening here, if you plotted this in time domain, if you plotted power as a function of time, it would be 18 watts average power. That's what P is, and the power signal would be going like this. That's the best you can do. We're only sending power. We're not receiving any power. It never drops below the axis here. So that's the most efficient that we can get. Okay, that was part part A and B. We calculated Z of the load, which is 20 minus 10J, and that's going to result in a 20 ohm resistor dropping 18 watts. Okay, 20 ohm resistor in wherever the impedance was. Didn't really write it down, but this is it. This is Z sub load. It's the answer for that. Okay, then they want to know, well, what if you don't have a candied end cap? You can't. What if? See, ideally, you want to balance the impedance of the load, which is J10, with minus J10, reactance. You want these two to cancel. But what if you can't do that? What if you're out of capacitors, which is typical. Like we don't always have we're trying to use power. That's why people want energy, so they can do this P thing, but they don't always take the time to fiddle around with, the reactance part of this thing. So what if you didn't do that? So that's part C and D. So part C and D, once again, this L load thing is only going to be resistive, and what's the best we can do there? So this is part C. So part C, I'm just going to rewrite the question. If load is purely resistive, and we still want max, basically, we still want max P, but we only have resistance to work with. So we have to use this, from the text, this little trick. We have to use R sub L is magnitude of Z sub 7. So this is another like trick. Okay. This is like your next best situation if you can't balance the reactance with reactive components. Then this is the next thing. Set your load to be the magnitude of Z sub 7. And so I'm just going to redraw this just for clarity here. So I got my Thevenin equivalent circuit. It looks like a 20 ohm resistor and a J10 inductor, and then there's nodes A and B. But now R sub load is just a resistor. It's not a. It doesn't have an inductance. And what is this value? It's so R load is the the magnitude of Z sub Thevenin, and Z sub Thevenin is it's 20 plus J10 magnitude, which is, this is rectangular. We never did figure out that in polar, but if you did convert that to polar, it'd be 20. We did somewhere. I don't know. But here it is, 22.36 angle 26. Seems like we did that. So the magnitude of that is just 22.36. So that's where this thing comes from, 22.36. That's R sub L. That's the special condition from the text. Just use use that number right there, the polar magnitude of the load of the source impedance. So the rest of the problem is the same now. So I is same as what we did over here. We're using Ohm's law. So the new I, different I now, I phasor, the new one is going to be V over the Z total now. With the Z total is different. So V is the same, it's 53 angle minus 26. And the Z total is 20 plus 22, it's 42.36 plus J10. So that works to be 1.23 angle minus 39. And the power to R sub L is, we have to use this IRMS, same IRMS R. So it's going to be this peak value, over root 2 is the converting peak I to IRMS, square that, times 22.36 is 17 watts. So, if you plotted that, that's kind of an interesting result. What it means is that the average power P is 17. This is P as a function of time, and the power, the peak power, the time domain power, the complex power, we didn't calculate, but if you did, you would see that it dips below here. So this stuff in here is due to reactance. Okay, and we're sort of wasting. The system's not running that efficiently. We're sending power back and forth because some of it's getting sort of, I don't know how to say it, hung up in this inductor. All right, so some concepts, some trick things. It's a good problem.